Greetings everyone, I am Lakshay Ganotra, leader of team ASTROFORGE, and we are submitting our qualification round task provided by ISRO's IROC 2025 challenge. Project ANAV Autonomous Navigation Aerial Vehicle is a pioneering endeavor crafted by team ASTROFORGE to meet the Martian-like challenges. Designed to compete in harsh weather-like conditions for Martian terrain, ANAV is equipped with movable landing gear mechanism, lightweight carbon fiber structures, and a complete GPS-denied algorithm for autonomous navigation. Team ASTROFORGE comprises of 10 innovators, meticulously researched, designed, and integrated each and every part of the space-grade aerial system, from designing STM32-based customized flight controller to developing the GPS-denied navigation algorithm. Each and every module is completely indigenously made. Our team has made a configurator named Akash Setu, which will be used for configuration of our aerial vehicle. A stable flight algorithm integrating PID and space matrix modeling. A linear actuator mechanism for retractable arms, which will be used for adaptive landing at slopey terrains. And much more were handcrafted during the whole process. Now my further teammates will give you descriptive analysis of overall project. Thank you so much.
Hello URC, now we are going to discuss about the design aspect. Our team has made sure that we have a certain checklist. Firstly, coming to the aerodynamics, our drone should have enough capabilities which is like reducing maximum obstacle while flying, like improving the thrust and lightweight, as well as more rigid. So we have opted completely carbon fiber frame, which is very rigid and as well as lightweight as per our requirement. So apart from that, we have made retractable landing gear, which is highly efficient for uneven surfaces, which has enough capabilities to from the gusts and storms as well. So this is the design, which is completely assembled with the electronics. You can look over it. So moving forward, our electronics team will explain in detail regarding the electronics.
So now moving on to hardware part and electronics part. Over here we are having a flight controller and a Raspberry Pi, which is a companion computer, and power module, and optical flow sensor, and ESCs and motors. So talking about flight controller, it is the main controller of the drone, which will control all the orientation and movement of the drone. So, and companion computer, we are using Raspberry Pi, which will take the surrounding data and which will directly give the signal to the flight controller, which will directly control all the functioning. So now moving forward, we are using an optical flow sensor over here, which will detect the change in pixel, brightness and pattern, and will automatically give the signal to the main flight controller and controls the holds the position. So now moving on to communication part, we are using telemetry. As per the competition rules, we are transmitting all the necessary data like sensor data and all the drone data.
So now we are providing an in-depth look at the software architecture behind our system. We will explore in core functionalities, key algorithm, and how it integrates seamlessly with our hardware components.
That's right, our software plays a crucial role in processing sensor data, making real-time decisions and ensuring precise flight control. Let's break it down step by step.
Okay, so our software is structured into three main layers: firmware, middleware, and application layer. Each layer has a specific role in ensuring efficient system operation. The firmware layer interacts directly with the hardware, managing data acquisition and motor control. About that, the middleware processes sensor inputs, applying filter techniques for improved accuracy. Finally, the application layer is responsible for high-level decision making. This is where mission planning, navigation, and autonomous flight adjustment take place.
One of the most critical components of our system is sensor fusion, which combines data from multiple sources like IMU and magnetometer to enhance positioning accuracy. We achieve this using extended Kalman filter and advanced algorithm that refines sensor data minimizing errors and improving overall stability. For stable stability, smooth maneuvering, and we implement a PID controller. This continuously adjusts flight parameters to maintain balance and precision. For navigation, we utilize A-star algorithm, which calculates the optimal flight path while avoiding obstacle dynamically.
Now let's talk about real-time processing. Our software processes incoming sensor data in milliseconds, ensuring rapid response to our environment changes. Another critical aspect is integration with Pixhawk, our flight controller. Before development, we perform a comprehensive calibration using Akash Setu, ensuring all sensors, including the IMU and magnetometer, function with maximum precision. This calibration process enhances flight accuracy and allows the system to adapt dynamically to different environments.
So in summary, our software is designed for precision, stability, and real-time performance. Every component works together to ensure reliable and intelligent system operation. That is.
Greetings guys, so I'll be starting with the analysis part of this drone. I have divided it into two parts to ease it for you. First will be the mechanical or the structural analysis of the drone, and second will be the electronics part of the drone. So first of all, to understand the mechanical analysis of the drone, we have to understand how does basically a flying object or a drone works. So there are three principal motions that we try to control here, which are the yaw, pill, and yaw, roll, and pitch of this drone, which we're doing using a flight controller. As far as the testing of this drone is concerned, for the design to get finalized, we had to make multiple iterations of the design, which was tested using CFD based finite element analysis software, using, for example, ANSYS as the software which we used to finalize the design. We went through multiple iterations of the design, and then we finalized this as the most stable design. This was for the mechanical analysis part of the drone. As far as the second aspect, which is the electronics analysis of this drone and making all the tests possible, basically for us to come to a final algorithm when it came to achieving all the test points, we had to do multiple tests, for which we use not this but multiple other frames as well. Videos of all the tests have been attached as the link further. So as I said, that as far as the electronics analysis of this drone is concerned, we use ROS based simulation software for drone, where we could load in our script and test how the drone is performing, and then we went into physical testing for the drone. So we did multiple iterations of various fail safes, for example, battery or no contact. So that is how most of the analysis of this drone was done, both in the physical world and on the electronics part of it. Thank you.